Hi guys, I'd like to introduce section 4.4, which is titled The Shape of a Graph, and I really like to think of it as what is concavity. In section 4.3, you talked about the first derivative test and what the first derivative can tell you about the shape of a graph, whether the graph is increasing or decreasing. And section 4.4, what is concavity, we're going to use differentiation to tell us more particular information about the shape of a graph. To start, I want to draw a function that we should know well on the interval from 0 to 2 pi. I'm going to draw the sine function, and I'm going to draw those benchmark points. We know that the sine function, let's label this f of x equals the sine of x. The sine function is 0 at 0 radians. It outputs a value of 1 at pi over 2 radians and negative 1 at 3 pi over 2 radians. I skipped pi. Sine is 0 at pi, and it's back up to 0 at 2 pi. So here's essentially what that sine function looks like. And I'm trying to draw it real rounded and curvy because what I want to show you is easier to see when I stretch that graph out along the x-axis. Okay, so if this is the function f, and we were to take the derivative and evaluate it at this x value, whatever x value that is here, what we'd find is that the derivative would evaluate to be positive. Why do we know that without even trying it? The slope of this tangent line is positive. Let's take the slope of the tangent line a little farther on. It's still positive, but it's a little bit less steeply sloped. Here, the slope of the tangent line is no longer positive. The slope of the tangent line is 0. Our tangent line is flat there, or horizontal. And so we're going from steeply sloped, less steeply sloped, 0 slope. If we continue moving to the right a little bit, now our tangent line is a line with negative slope. So the slopes of our tangent lines, the slopes as we move to the right, are smaller. Maybe not in magnitude, but as far as sine goes, the slopes are moving. As we move to the right on the graph of f, the slopes are going from big positive, a little bit less big positive, 0 to negative. So the first derivative, which is what gives us the slopes of the tangent lines, the first derivative is decreasing over this interval from 0 to pi. So we still have negative slope here. And then notice at pi what is happening. We still have a negative slope. And after pi, we still have a negative slope and a negative slope, but it is a bit less negative. Those are less steep negative slopes. And then we come back up to a 0 slope, and then we start with a positive slope. I'm sort of swaying my tangent lines to emphasize you're really just looking at the SIGN sign, the SIGN sign of that slope. And on the interval from pi to 2 pi, my slopes are big negative, negative, less big negative, 0 slope, positive slope. So I'm going from, slopes are going from negative to positive on the interval to 0 to 2 pi. So let's note that. Slopes are increasing from negative to positive on the interval from pi to 2 pi. And back here on the interval from 0 to pi, on 0 to pi, we saw that the slopes were getting smaller or decreasing. And so now what I want you to notice is the shape of the original function. We're talking about the original function. The slopes are given by the first derivative, and then we're also talking about the rate at which the slopes are changing. which would indicate the second derivative. We're taking a rate of change of the first derivative, which would be the second derivative. Now just look at the function. On the interval from 0 to pi, that function's like your cereal bowl turned upside down, where it would spill all your milk and all your cereal. We call this sort of shape of the function concave down. And then on the interval from pi to 2 pi, the function looks like a cereal bowl that would hold milk. We call it concave up on this interval. Let those words have a meaning to you. Let your intuition take over. This is concave down. It's downturned. This section of the graph is concave up. It's upturned. So that's our intuitive look at what concavity is. And in the next short video, we'll look at the definition of concavity, because of course this is mathematics and we want to mathematically precisely define that notion, and then how to test for concavity using the second derivative.